Use the addition method to find the simultaneous solution. Looking at my system of equations, I think it would be best to try to eliminate the y's because I notice my y has a coefficient of -1. It might make it easier to make these coefficients opposites. So if I choose to eliminate y, I want to look at the coefficients to start off with. So it's going to be -1 and -3. And my goal is to make the coefficients opposites. So if I'm looking at a number that both 1 and 3 go into, my goal would be to turn the coefficients into 3 and -3. So when I'm looking at the coefficient that I already have versus what I need, one of them already has a -3, and that's the second equation. So that means we're not going to have to modify that second equation. I now want to look at how do I turn -1 into +3. And that would mean that I would need to multiply -1 by a -3 so that I can make a +3. So that means this first equation is going to get modified by multiplying both sides of the equation by -3. So multiplying the first equation by -3, I will get -6x plus 3y equals -9. I don't have to modify the second equation, so I will just rewrite it. And now keep in mind that we had first decided to eliminate the y's, so we want to make sure our coefficients are opposites. +3 and -3 they are. So now we're ready to add. Now something very interesting happens when we add these two equations. Not only will our y's cancel out like we thought they would, but it also happens that our x's cancel out as well. When that happens, you have the left-hand side equaling 0. And then the right-hand side, you'll notice that -9 plus 9 also equals 0. So here we have a peculiar case where all the variables canceled out. And when that happens, you could have one of two cases. The first case, you might notice when you're looking at what's left over after it's been canceled, we have 0 equals 0, and that happens to be a true statement. So that case will give us the fact that we actually have the same line. So the way our book refers to it is they just say, well, if you want to name the solution to the system, you can say that you have the same line. And solutions to systems that are the same line, the solution is all points that lie on either line. So remember, when you're solving systems of equations, the goal is to get a simultaneous solution. When cases like this where all variables cancel out and you're left with a true statement, you have the case of a same line, and same lines all of their points are common, but only the points that lie on the line are the simultaneous solution. So you can address it in one of two ways. When you want to say what the answer is, you can either say same line, or in English, you can say all points that lie on either line. Now, although we got the same line for the solution to the previous example, we might be asking, what if all the variables cancel out and we got a false statement? And so what if you got something like 0 equals 7? That would be considered false. In cases like this, if you get a false statement, you have the case of parallel lines. And if you remember from the previous sections, parallel lines have the same slope, and that means they will never intersect no matter how far into the axes we look. So if parallel lines never intersect, that would mean they have no points in common, therefore meaning that there would be no solution to a system like this.